cosmic whisper, a 200 million-year-old mystery solved? It's a question that has been puzzling astronomers for nearly 2 decades. Fast radio bursts, or FRBs as they're commonly known, are one of astronomy's most perplexing phenomena. These bursts of radio energy last just milliseconds, yet they contain more energy than our sun produces in decades. The first FRB was discovered in 2007 by astronomer Duncan Lorimer while reviewing archival pulsar survey data from the Parkes Radio Telescope in Australia. What he found was something bizarre, a powerful radio burst that lasted just 5 milliseconds, but had traveled an estimated 3 billion light-years to reach Earth. Since then, astronomers have detected over 600 FRBs, with new ones being discovered almost daily. Most of these cosmic flashes appear once and never repeat, vanishing as quickly as they arrived. Others, known as repeaters, flash multiple times from the same location in the sky. This inconsistency has made them particularly challenging to study and has fueled intense debate about their origins. The mystery deepened in 2022 when astronomers detected FRB 220610A, the most distant FRB ever observed. This particular burst traveled approximately 8 billion light-years to reach us, meaning it was emitted when the universe was just over a third of its current age. When we look at objects this distant, we're essentially looking back in time, seeing the universe as it was billions of years ago. It's like receiving a telegram that was sent before dinosaurs walked the Earth, before the continents took their current shape, before most of the stars in our night sky had even formed. What makes this particular FRB so significant is not just its impressive distance, but the information it carries. By studying the signal's dispersion, how the radio waves were spread out by the intergalactic medium they traveled through, astronomers have gained new insights into the distribution of matter in the universe. This cosmic whisper might help solve one of cosmology's most persistent problems, the missing baryon problem. According to our current models of the universe, about 5% of its total mass energy content should be in the form of ordinary matter, the stuff that makes up stars, planets, and everything we can directly observe. This matter is primarily composed of baryons, which are particles like protons and neutrons. But when astronomers count up all the visible baryons in the universe, they consistently come up short, finding only about half of what should be there. The leading theory is that these missing baryons are hiding in the vast, diffuse filaments of hot gas that connect galaxy clusters, the cosmic web. But this gas is so thin and diffuse that it's nearly impossible to detect through conventional means. This is where FRBs come in. As these powerful radio signals travel through the cosmic web, they interact with the free electrons in this diffuse gas, causing the signal to disperse. Different frequencies arrive at slightly different times. By measuring this dispersion, astronomers can essentially weigh the material the signal passed through. It's like using radio waves as a cosmic scale. The recent analysis of FRB 220610A provides strong evidence that these missing baryons are indeed hiding in the cosmic web, potentially solving a mystery that has persisted for decades. But where do these enigmatic signals come from in the first place? What cosmic event could possibly generate such immense energy in such a short time? This has been the central question driving FRB research, and we're finally starting to get some answers. The leading theory points to magnetars, incredibly dense neutron stars with magnetic fields trillions of times stronger than Earth's. These stellar remnants are formed during the explosive deaths of massive stars. A teaspoon of neutron star material would weigh billions of tons on Earth. Their magnetic fields are so intense that they would be lethal to humans from thousands of miles away, literally tearing apart the atoms in your body. The breakthrough came in April 2020, when astronomers detected an FRB-like burst coming from within our own galaxy, specifically from a known magnetar called SGR 1935 plus 2154. This was the first time an FRB had been linked to a specific source, and it provided compelling evidence for the magnetar theory. The burst wasn't as powerful as the extragalactic FRBs we typically observe, but scaled for distance, the energy profiles matched remarkably well. But how exactly do magnetars produce these bursts? One possibility is through starquakes, massive seismic events on the magnetar's surface. The crust of a neutron star is incredibly rigid, composed of a lattice of atomic nuclei and electrons compressed to extreme densities. As the powerful magnetic field evolves and shifts, it puts stress on this crust. Eventually, something has to give, and the crust cracks in a violent, sudden release of energy, a starquake. This disruption could temporarily disturb the magnetar's magnetosphere, triggering a powerful release of radio waves that we detect as an FRB. Another possibility involves magnetic reconnection, a process where magnetic field lines break and reconnect in a new configuration, releasing massive amounts of energy in the process. This is similar to what happens in solar flares on our sun, but on a magnetar, the process would be millions of times more energetic. These reconnection events could occur in the magnetar's atmosphere or in the surrounding plasma, producing the brief, brilliant radio bursts we observe. What's particularly fascinating about FRBs is that they appear to come in different flavors. Some, like the famous repeater FRB 121102, emit bursts multiple times in irregular patterns. This particular source has been observed emitting hundreds of bursts since its discovery in 2012. Others seem to be one-off events, never to be seen again. This diversity suggests there might be multiple mechanisms at play, or that we're observing different stages in the life cycle of magnetars. In 2022, astronomers made another startling discovery, an FRB that lasted for about 3 seconds, roughly 1,000 times longer than the typical burst. This signal, designated FRB 209221A, contained a series of regular repeating peaks, almost like a heartbeat. This periodic pattern hints at a rotating source, providing more clues about the physical processes behind these mysterious signals. The study of FRBs has been revolutionized by new dedicated instruments like CHIME, the Canadian Hydrogen Intensity Mapping Experiment. Located in British Columbia, this revolutionary radio telescope was designed primarily for cosmological research, but has proven to be an FRB-finding powerhouse. Since it began operations in 2018, CHIME has detected hundreds of FRBs, dramatically increasing our sample size and allowing for statistical studies that were previously impossible. CHIME's success lies in its design. Unlike traditional dish telescopes that observe a small patch of sky at a time, CHIME has no moving parts and observes a large swath of the northern sky every day as the Earth rotates. This gives it an unprecedented field of view, making it ideal for catching rare, transient events like FRBs. The telescope consists of 4 cylindrical reflectors, each 100 meters long, that focus radio waves onto an array of receivers. These receivers are connected to a powerful specialized supercomputer that processes the incoming data in real time, looking for the distinctive signatures of FRBs. As our detection capabilities improve, we're starting to find FRBs in greater numbers and with greater precision. This has allowed astronomers to start addressing another intriguing question. Are FRBs evenly distributed throughout the universe, or do they cluster in certain types of galaxies or environments? The findings so far have been illuminating. FRBs appear to come from a diverse range of host galaxies, from massive ellipticals to dwarf irregulars, from galaxies with active star formation to those where star formation ceased billions of years ago. This diversity complicates the picture somewhat. If all FRBs come from magnetars, and magnetars form from the deaths of massive stars, we would expect to find them predominantly in galaxies with recent star formation. The fact that we don't suggests either that magnetars can form through multiple pathways, or that there might be additional sources of FRBs beyond magnetars. One particularly interesting case is FRB 22020E, which was traced to a globular cluster associated with the nearby galaxy M81. Globular clusters are ancient collections of stars, typically billions of years old, with very little ongoing star formation. This is an unexpected environment for a magnetar, which are generally thought to be relatively young objects. This discovery suggests that some magnetars might form through alternative channels, such as the merger of white dwarfs or through accretion-induced collapse of white dwarfs that have accumulated too much mass. Beyond their astrophysical importance, FRBs have also proven to be valuable cosmological tools. The universe is expanding, and the rate of this expansion is described by a value known as the Hubble constant. Measuring this constant precisely is one of the most pressing challenges in modern cosmology, as different measurement techniques have yielded slightly different values, a discrepancy known as the Hubble tension. FRBs offer a new, independent way to measure the Hubble constant. By combining the dispersion measure of an FRB with the redshift of its host galaxy, astronomers can derive an estimate of the Hubble constant. As we discover more FRBs and precisely locate their host galaxies, this technique could help resolve the Hubble tension, providing crucial insights into the fundamental nature of our universe. The search for FRBs has also spurred technological innovation. The need to process vast amounts of data in real time has led to the development of specialized computing systems and algorithms. These advances have applications beyond astronomy, influencing fields from telecommunications to medical imaging. This is a common pattern in science. The pursuit of fundamental knowledge often yields practical benefits in unexpected areas. As we look to the future, several next-generation facilities are poised to revolutionize FRB research. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the world's largest radio telescope when completed. With unprecedented sensitivity and survey speed, it's expected to detect thousands of FRBs per year, potentially identifying patterns and rare subtypes that have eluded detection so far. Another exciting prospect is using machine learning and artificial intelligence to sift through the growing catalog of FRBs. These tools can identify subtle patterns and correlations that might escape human analysts, potentially revealing new insights about the nature and origins of these enigmatic signals. Already, machine learning algorithms have been employed to distinguish genuine FRBs from radio frequency interference in telescope data, significantly improving detection efficiency. The story of FRBs is a testament to the serendipitous nature of scientific discovery. What began as an unexpected signal in archival data has blossomed into a vibrant field of research, connecting disparate areas of astronomy and cosmology. It's a reminder that the universe often surprises us, and that these surprises can lead to profound insights about the cosmos we inhabit. As we continue to listen to these cosmic whispers, we're not just solving the mystery of their origins, we're using them as probes to explore the vast, largely invisible structures that permeate our universe. FRBs have already helped us locate the missing baryons, may soon help resolve the Hubble tension, and could potentially reveal previously unknown phenomena in the extreme physics of neutron stars. The universe speaks to us in many ways, through the gentle twinkling of distant stars, through the majestic spirals of galaxies, and sometimes through brief, powerful bursts of radio energy. By learning to interpret these signals, we deepen our understanding of the cosmos and our place within it. The mystery of fast radio bursts isn't fully solved, but we're closer than ever to understanding these enigmatic cosmic messengers. What began as a cosmic whisper is gradually becoming a clearer voice, telling us stories of violent stellar deaths, incredibly dense objects with magnetic fields beyond comprehension, and the vast, hidden architecture of our universe. As our technology advances and our sample of detected FRBs grows, these stories will become richer and more detailed, potentially answering questions we haven't even thought to ask yet. This is the beauty of fundamental research. It expands not just what we know, but what we know we don't know, constantly pushing the boundaries of human understanding into new territory. The mystery continues, but with each new detection, each new analysis, we're peeling back the layers of this cosmic puzzle, getting ever closer to the truth hidden within these fleeting signals from across the cosmos. The 200-million-year-old mystery isn't completely solved, but its whispers are becoming increasingly clear, revealing new facets of our magnificent universe.